So these massive language models can do some truly mind-blowing things, right?
Absolutely.
Generate text, translate languages. It feels like the future is here. But if you've spent any time really digging into their output, you've probably noticed they can also confidently spout nonsense, make up facts.
Yeah.
It's like they're incredibly articulate, but sometimes their information source is, well, thin air.
It's a fascinating limitation, isn't it? They're trained on these colossal data sets and build this intricate web of knowledge within their parameters.
Mm-hmm.
But that knowledge is static,
Right. Fixed.
fixed at the point of training.
Yeah.
Accessing it and, crucially, updating it can be a real challenge.
Exactly. Now imagine a way to give these superintelligent systems a live connection to a vast, constantly updating library of information. That's sort of the core idea behind something called Retrieval-Augmented Generation, or RAG.
Mhm.
Think of it as equipping that brilliant student with instant access to all the research materials they could ever need right when they need them.
That's a really insightful way to put it. Our bag models essentially bridge that gap.
Yeah.
They take the text generation prowess of a pre-trained language model
Yeah.
and combine it with the ability to search and retrieve information from an external knowledge base.
And today, we're diving deep into how this all works. We've got a fantastic research paper that really unpacks the mechanics and the potential of RAG.
That's right. Our main focus for this deep dive is the paper Retrieval-Augmented Generation for Knowledge-Intensive NLP Tasks.
Yeah.
They met a few years ago and really laid the groundwork demonstrating just how powerful this approach could be.
So our mission really is to understand the nuts and bolts of RAG, to see how it tackles those knowledge gaps we've been talking about, and to maybe even uncover some surprising capabilities along the way.
Sounds good.
Okay, let's unpack this. What's the central concept driving our RAG?
At its core, a RAG model operates with two key types of memory. First, there's the pre-trained language model itself. The paper calls this parametric memory.
Parametric, okay.
Yeah, it's the knowledge the model has absorbed and stored within its billions of connections during its initial training. It's like the foundational knowledge our super smart student brings to the table.
And the second type is the non-parametric memory. Is that the external part?
Precisely. This is the external reservoir of information. In the research, they used a dense vector index of Wikipedia.
Okay, dense vector index. What does that really mean in practice?
Well, imagine every piece of information in Wikipedia is converted into a unique digital fingerprint, like a vector. The query your question is also fingerprinted using the same method.
Ah, okay.
And the system then quickly finds the fingerprints in the index that are most similar to the query's fingerprint. These represent the most relevant bits of information. Think of it as that vast library our student can instantly search.
Got it. And the paper mentions using BART and DPR. Can you break down how those specific models fit into this picture?
Absolutely. So they utilize BART, which is a really strong pre-trained sequence-to-sequence model known for its ability to generate text. That serves as the parametric memory.
The generator.
The generator, exactly. The engine that ultimately produces the answer. And for accessing the non-parametric memory, that Wikipedia index, they use something called DPR.
DPR.
R-dense passage retriever. Think of DPR as the super efficient librarian. Its job is to find the most relevant documents or passages in that Wikipedia index based on the input query.
Okay, so BART generates, DPR retrieves. And figure 1 in the paper really gives you a visual of this whole process, doesn't it?
It does, yeah.
You input a question, it goes through an encoder, gets matched against the document index, the retriever pulls out relevant bits, and then the generator uses all of that to create the output.
Exactly. That figure shows the initial query being transformed into that digital representation, that vector, which is then used to probe the document index for similar representations. The retriever, DPR, then returns the top few most relevant documents. And here's the crucial step. The generator, BART in this case, takes both your original question and these retrieved documents as context to formulate its final answer.
So it's not just copying and pasting from Wikipedia. The generator is still using its own understanding of language to synthesize an answer based on what it found.
Precisely. And what's particularly clever, I think, is that this entire process from finding the relevant information to generating the answer can be trained end to end.
Okay, end to end.
Both the retriever, the librarian, if you will, and the generator are jointly fine-tuned. They learn to work together on specific tasks.
End-to-end training sounds complicated, though. How does the model learn to retrieve the right things if the retrieved document is just an intermediate step? It's not the final answer it's graded on, right?
That's a great question. The trick is that during training, The retrieved document is treated as what's called a latent variable.
Latent variable.
Right.
Okay.
Think of it like teaching a student to find the right book in the library to help them answer an essay question. You don't grade them on which specific book they pick initially, but on how good their final essay is, using the information for whatever book they chose.
Ah, I see.
The right book is the latent variable that helps them get to the good essay. Similarly, the ARG model learns to retrieve documents that, when fed to the generator, ultimately lead to the best possible, most correct final answer for the given question. It optimizes the whole pipeline towards that goal.
Okay, that analogy helps a lot. So the model essentially figures out what kind of information it needs to pull to help it nail the final answer. Now, the paper talks about two different ways R can be set up, RAG sequence and RAG token. What's the key difference there?
Right, this is where it gets really interesting in terms of how it uses the retrieved info. ARG sequence is maybe the more straightforward approach.
Okay.
In this setup, the model takes your question, retrieves one set of the top few most relevant documents, maybe say the top 5 documents, and then it uses those same documents as its information source for generating the entire answer. It's like picking a few key articles and sticking with them for the whole response.
So it finds its sources up front and then builds the answer based only on those.
Exactly. Our RAG token, on the other hand, is much more dynamic. It has the ability to retrieve a different set of top documents for each token. Basically, each word it generates in the answer.
Wait, for each word? Seriously?
Yeah, so as it's constructing its response, word by word, it can continually look up and pull in new information relevant to the specific part of the answer it's currently working on.
Wow, that sounds incredibly flexible. It's like it can piece together information from a much wider range of sources as it goes along.
That's the idea. It allows for a much more nuanced and context-aware use of the external knowledge. It could potentially draw on different facts from different documents for different clauses within a single sentence.
That's quite sophisticated. So we have these two RAG models, sequence and token, and they both rely heavily on these pre-trained components, DPR for finding information and BART for generating text. Why is using these pre-trained models such a big deal? Why not train from scratch?
Well, using pre-trained models provides a huge advantage. It saves enormous amounts of computation, for one, but it's also about performance. Think about it. Models like BERT, which DPR uses, they've already been trained on massive amounts of text. They already grasp the nuances of language, word relationships, even a lot of factual knowledge embedded in that text.
Right, they have a head start.
A massive head start.
Yeah.
And DPR itself was specifically pre-trained further to get good at retrieving documents relevant to questions from data sets like Trivia QA, natural questions. So it already has a pretty good sense of what a relevant document looks like for different kinds of questions.
So it's not starting from zero. It already has a strong foundation in understanding language and how to look for information effectively.
Precisely. And similarly, BART, the generator, has been pre-trained with a focus on understanding context and generating coherent, fluent text. By leveraging these pre-trained powerhouses, the RAG architecture doesn't need to learn everything from the ground up.
Makes sense.
It already has a strong baseline understanding of language and information access, which significantly cuts down on the amount of task-specific training needed to get really impressive results.
It's like having a team of highly skilled specialists who already possess core knowledge, and you're just training them to collaborate better on a specific project. That makes perfect sense. So given all this sophisticated architecture and the pre-trained components, what kind of results did these R models actually achieve? Did they really move the needle in terms of answering questions and generating text?
Oh, the results were genuinely groundbreaking at the time. On several challenging open domain question answering tasks, these are tasks where the model has to find the answer in a huge collection of documents like Wikipedia.
Like natural questions, web questions.
Exactly. Natural questions, web questions, curated trek. On those, the R-ing models achieve state-of-the-art performance. They actually outperformed purely parametric models like T5.
Which rely only on internal knowledge.
Right. T5 just uses its internal memory. R-ing beat those. And maybe more surprisingly, it also beat task-specific retrieve and extract systems, like the DPR model used just for QA, which are designed only to find and pull out answers from documents.
Wow.
Table 1 in the paper really showcases these impressive gains.
That's a major leap forward.
Yeah.
So RAG was not only better than models that just relied on their internal knowledge, but also better than systems specifically built just to find answers in external sources.
Yes. And here's a really interesting point the paper highlights. ARA can even generate correct answers in situations where the exact answer string isn't explicitly stated word for word in any single retrieved document.
How does it do that?
By synthesizing. For instance, on the natural questions dataset, it achieved almost 12% accuracy in such cases where the answer had to be inferred or combined from the text. An extractive model, which can only pull out existing text spans, would score 0 in those scenarios.
Right.
This demonstrates a crucial ability of RAG to synthesize information, to reason across the retrieved text, not just retrieve it verbatim.
That's a huge advantage. It shows real understanding. What about when the task is less about finding a specific fact and more about generating a longer, more abstractive answer, like summarizing or explaining?
RAG also showed strong performance on abstractive question answering. They tested it using the MS Marco dataset. And Table 2 indicates that RAG outperformed the baseline BART model, just BART on its own, even when RAG didn't have access to the gold passages.
Bold passages meaning.
The specific documents known to contain the answer, which other top-performing models on that task often use during training, or even sometimes at test time. RAG did better without that advantage.
So again, it's showing it's effective at actually using the retrieved knowledge for more complex generation.
Exactly.
Now, one of the examples that really stood out to me was the application to generating Jeopardy questions. That seems like a particularly challenging, kind of creative task.
It is. Jeopardy's tough. You're given the answer, the clue, and the challenge is to generate the precise, factual question in that specific Jeopardy style that would lead to that answer.
Right. What is or who is?
Exactly. The researchers found that RAG token, the more dynamic version, outperformed plain BART, which is itself a very strong generation model, on a metric called QBLUU1.
QBLEU1.
Yeah, it's a variant of the BLEU score often used for generation tasks.
Yeah.
But this one puts a higher value on matching key entities' names, places, dates within the generated question.
Okay, so it measures factual accuracy in a way, and it wasn't just about these automated scores, right? Didn't they have humans evaluate the quality too?
They did, yes. And that's often more revealing. The human evaluations, which are detailed in Table 4, show that the questions generated by RAG token were consistently perceived as being more factual and more specific compared to those produced by BART alone.
Interesting.
This really highlights RAG's capability in generating knowledge-intensive text that actually holds up to human scrutiny for accuracy and relevance.
The paper uses a really insightful Hemingway example to illustrate how RAG token specifically operates. Can you walk us through that one?
Certainly, it's a great illustration. So, when RAG token was tasked with generating a Jeopardy question for the answer Hemingway, the model, as shown in Figure 2, seemed to draw upon different Wikipedia articles for different parts of its output.
Okay.
For example, when it started generating the title The Sun Also Rises, the analysis suggested it was heavily relying on a specific retrieved document that mentioned that particular book.
Mm.
Then, later in the same generated question, when it mentioned A Farewell to Arms, a different retrieved document appeared to become more influential.
So it switched sources mid-generation.
It looks like it, yeah. But the really interesting part, as you mentioned, was that after maybe the first word or so of each book title, the model's reliance on those specific retrieved documents seemed to decrease significantly.
What does that suggest?
It suggests that the generator, BART, was able to tap into its own internal parametric knowledge, its stored understanding of language and common phrases, to complete the well-known titles once it had a strong starting point, like the first word, provided by the retrieved information.
Ah, okay.
It's a fantastic demonstration of how the external non-parametric retrieval initially guides the generation, surfacing specific knowledge nuggets
Great.
that the internal memory can then elaborate on and complete fluently. It's like the external knowledge gives it the key factual pieces, and then its internal language knowledge helps string them together properly.
It's like the retrieval system primes the pump with a core fact, and then the powerful language model can really take over to phrase it correctly and finish the thought. That's really neat.
It really is.
What about tasks like fact verification, where you need to determine if a statement is true or false based on evidence? How did RAG perform on something like the Fever dataset for that?
On the Fever task, which involves classifying claims as supported, refuted, or not enough info based on evidence found in Wikipedia, Orgagi's accuracy was surprisingly close to the state-of-the-art pipeline models at the time.
And those pipeline models are usually quite complex, right? Often involving multiple stages.
Exactly. And what's particularly remarkable, I think, is that RAG achieved this competitive performance without having explicit supervision telling it which specific documents or sentences it should retrieve as evidence.
So it wasn't trained on here's the claim, here's the perfect evidence sentence?
No, unlike many other top-performing fever models, which often rely on that kind of supervision, RAG just learned implicitly what kind of documents were useful for making the final classification. And the researchers also observed a high degree of overlap between the documents that RGAG independently chose to retrieve and the actual gold evidence documents identified by humans in the fever dataset.
So it was naturally finding the relevant evidence needed to verify or refute a claim, even without being explicitly told what evidence to look for. That's a really powerful capability.
It really is. It shows it's learning something fundamental about evidence relevance.
The paper also touches briefly on the diversity of the generated text. It mentions that RAG tends to produce more varied outputs compared to BART alone. Why is that necessarily a good thing?
Well, generation diversity is really important for preventing language models from becoming repetitive or predictable. You don't want the same canned phrases all the time.
True.
Table 5 in the paper shows that RAG sequence, in particular, tended to produce a wider range of distinct enneagrams, basically unique sequences of words in its generated texts compared to BART. This suggests that by having access to a broader, more diverse set of information through retrieval, RAG can potentially generate more creative, nuanced, and less monotonous outputs.
Okay, that makes sense. Now, the researchers conducted some ablation studies. These are experiments where you remove or change parts of the system to see how important they are, right?
That's right. Kind of like taking bits out of an engine to see what stops working.
What were some of the key findings from those studies about the RAG architecture?
Table 6 in the paper really highlights the critical role of that learned retrieval component, the DPR, when they tried two alternatives, either freezing the retriever during training, meaning it couldn't adapt its retrieval strategy for the specific downstream task.
So it just used its general pre-trained retrieval ability.
Exactly. Or if they replaced DPR entirely with a simpler, more traditional method based on keyword overlap like BM25.
Okay, like a classic search algorithm.
Yeah. In both cases, the overall performance generally declined across most of the open domain question answering tasks, compared to using the fully trained adaptable DPR.
So the smart learned retriever really matters for finding the best context.
It seems so for most broad QA tasks. However, it's interesting to note that for more entity-centric tasks like Fever, where matching specific names and entities is maybe more crucial, the simpler BM25 retriever actually performs surprisingly well, sometimes even close to DPR.
Huh. Maybe keywords are enough when you're just checking facts about specific people or places.
Possibly. But overall, for general question answering that requires deeper understanding, the learned retrieval capabilities of DPR prove to be a significant advantage for RAG.
And the index hot swapping experiment sounds incredibly insightful. Can you tell us more about that? It sounds really practical.
Oh, this was a really elegant experiment. Just beautiful. It perfectly illustrated how RAG's knowledge can be updated without needing to retrain the entire massive model.
Which takes forever and costs a fortune.
Exactly. So what the researchers did was simple. They just swapped out the underlying Wikipedia index, the non-parametric memory. They have one version built from a Wikipedia dump from December 2016 and another more up-to-date one from December 2018.
Okay, 2 years apart.
Yep. Then they posed questions to the same RAG model without any retraining, but just changing which index it was pointed at. The questions were about things like world leaders who had changed positions between those two dates.
Ah, clever. So, asking who was the Prime Minister of the UK using the different indexes, and what happened?
It worked just as you'd hope. RAG, when using the 2016 index, correctly answered questions based on the leaders in power in 2016. And when they switched it to use the 2018 index without any other changes, it correctly answered based on the 2018 leaders.
Wow.
But crucially, when the index and the year implied by the question didn't align, like asking about the 2018 leader using the 2016 index, the accuracy dropped significantly.
So it proved the knowledge was coming from the index.
Absolutely. It clearly demonstrates that RAG's factual knowledge is directly tied to the information within its non-parametric memory, and that memory can be updated simply by building a new index from newer documents. Think about that. No more massive, slow, expensive retraining cycles just to update a model's knowledge on current events or new discoveries.
That's a potential game changer for keeping these AI systems current and relevant, isn't it?
Huge implications. Just to update the library, not rebuild the librarian's brain.
Fascinating. Finally, the paper explored what happens when you let Argo retrieve more documents during the process. Is more always better? What did they discover there?
Good question. More isn't always necessarily better, or at least it's nuanced. Figure 3 in the paper shows the trends. For RGA's sequence on open domain QA tasks, Generally, retrieving more documents going from, say, 5 documents to 10 or 20 at the time of answering did lead to improved performance.
Okay, so for sequence, more context helped.
Generally, yes. However, for our gate token, the one that retrieves per word, there seemed to be a point of diminishing returns. Performance often peaked when retrieving around 5 or 10 documents per token, and sometimes retrieving significantly more, like 50 or 100, didn't help or even slightly hurt performance.
Why would that be? Information overload.
That's the likely explanation. While having access to more information can be beneficial, the model also needs to be able to effectively process and filter that information to extract what's truly relevant for that specific generation step. Our gag token is already doing a lot of retrieval, so maybe too many documents just adds noise.
So there's a balance to be struck between information access and the model's ability to focus on the most useful bits.
Exactly. It depends on the model variant and the task.
So pulling it all together, RAG seems to represent a really powerful new direction for building more knowledgeable and hopefully more reliable language models. What are the broader implications of this technology, thinking beyond just benchmark scores? And what kind of future research does the paper suggest?
Well, paper points out some really positive potential societal benefits. By grounding language models in actual retrievable external knowledge, RAG offers the potential for significantly increased factual accuracy.
Which directly addresses that hallucination problem we started with.
Precisely. Making things up becomes harder if you're checking against a source. It also potentially allows for better control over the information used in generation. You could, in theory, restrict the knowledge source, and it can improve the interpretability. You can sometimes point to the specific documents the model used to generate its answer.
That traceability is huge.
Absolutely. Imagine the possibilities for providing reliable information in fields like medicine or law, where accuracy and justification are paramount. You could potentially trust the output more if you know where it came from.
Definitely. Of course, like any powerful tech, there are always potential downsides or ethical things to consider too, right?
For sure. The paper touches on this in the broader impact section. Advanced language models, even grounded ones, could still potentially generate misleading content if the knowledge source itself is biased or flawed. And there are always concerns about automation impacts, privacy, if personal data were indexed, and so on. These are ongoing considerations for all powerful AI.
Right. It's not a magic bullet, but a step in a potentially better direction. And in terms of where this research might go next, what did the authors propose?
They proposed a really interesting next step: jointly pre-training the retriever and the generator together, right from scratch.
As opposed to using separately pre-trained DPR and BART.
Exactly. The RAG models discussed in this specific paper rely on those components that were pre-trained independently first and then fine-tuned together. The authors suggest that by pre-training a retrieval-augmented generation model truly end-to-end with a unified training objective from the very beginning, it might be possible to achieve an even deeper and more effective integration of the parametric and non-parametric knowledge. Kind of like teaching the librarian and the writer to think together from day one.
That makes intuitive sense. Could lead to even better synergy.
Potentially, yeah. It could unlock even greater gains in performance and perhaps efficiency down the line. It's an active area of research.
So to wrap up, RAG models really do seem like a significant leap forward in our collective efforts to create more knowledgeable, more dependable, and maybe more up-to-date language-based AI.
Absolutely. By intelligently combining the sort of innate language skills and world knowledge baked into pre-trained models with the ability to dynamically access and process a virtually limitless supply of external verifiable information, RAG offers a very promising pathway. It helps overcome some key limitations of standard language models.
And for me, looking back at our discussions, some of the real aha moments were seeing how RAG can synthesize answers, not just extract them answering questions, even when the answer isn't directly stated in one place.
Right, that synthesis is key.
The incredibly dynamic way RAG token can pull in different information piece by piece as it generates text, like in that Jeopardy example, and just how easily, conceptually at least, you can update its knowledge base by swapping out the underlying data source. That hot swapping idea is just really powerful.
It really is, and it makes you consider the future possibilities, doesn't it?
Yeah.
How might this kind of technology reshape things like, well, search engines, or the capabilities of the virtual assistants we talk to every day?
Or even fundamentally change the way we approach learning and accessing information ourselves in the coming years.
Exactly. And what are the ethical guardrails we need as these systems get better at generating factual-sounding, source-based content, especially if the sources themselves might have biases? Lots to think about.
It certainly does feel like we're on the cusp of a new era in AI where these hybrid approaches, blending different strengths like internal knowledge with external access, are going to unlock some truly remarkable capabilities. The evolution is definitely ongoing, and AI is a really exciting piece of that puzzle.